Hello everyone, thank you for being here and watching this video. I'm Hossein Golestani from the University of Michigan, and in this video I'm going to present HyperData, which accelerates data transfer in software data planes through targeted prefetching. I've done this work with my advisor, Professor Thomas Wenisch. So let's get started. Data centers and cloud computing are evolving at an amazingly rapid pace. Data-intensive applications are nowadays developed with a distributed microservice-based software model that involves much finer-grained inter-server communication as compared to a monolithic software architecture. As far as cloud computing is concerned, data center systems have increasingly more cores than before, and a single system may have several hundreds and even more than 1,000 tenants. This leads to another phenomenon, I/O virtualization, where a single physical I/O device like a network card or a storage device is shared possibly by many tenants or processes at the same time. At a level lower than the application level, today's I/O devices have tremendous throughput and microsecond scale access time, which is the time scale current systems are not good at, leading to the killer microseconds problem. Well, all these trends, among many others that demand scalability and resilience from the data center, involve frequent interaction of CPUs and I/O devices. So the performance of I/O and related software stacks is a crucial factor in the overall performance. In our discussion, a software data plane is the I/O software stack that performs transport processing and orchestrates data transport among I/O devices and tenants of a system, as shown in the figure. Data plane operations in conventional systems are done in the OS kernel, but for better performance, modern data planes bypass the kernel. Traditionally, an I/O device delivers the data directly to memory through DMA. Accessing data from DRAM obviously has a long latency, so technologies like DDIO allow a peripheral like a PCIe attached device to deliver data directly to the last level cache. But there are still several issues, such as not delivering the data to private caches or even the LLC bank closest to the consumer core, as well as polluting the cache in cases where only data item headers rather than payloads are needed. So necessary and only necessary data don't seem to be nearest to the core at the right time. To tackle these issues, we propose the HyperData Accelerator with the features shown here. HyperData prefetches data buffers as close as possible to the target core, that is, to the L1 cache. Only the required subset of data items, for example, network packet headers, are prefetched to avoid cache pollution. HyperData performs prefetching not only for data plane I/O communication, but also for data plane tenant, that is, core-core communication. Finally, various queue formats are supported, like regular or direct queues, virtual or indirect queues, and multi-consumer queues. At a high level, HyperData is composed of two components. First, a system-level monitoring set which watches for data arrival in the queues and triggers prefetch operations. Second, per core prefetchers, which actually perform the prefetch operations and are programmable to support different queue formats. As we will see at the end, with a small area overhead, HyperData can improve the processing latency by up to 2.4 times. Prefetching is predicated on knowing what memory references are likely to be made or will definitely be made in the near future. Data items in data planes are communicated through shared memory queues. What pass through the queues are in fact data item descriptors, which point to the corresponding data buffers. Accessing the whole part or a subset of a single data buffer involves reading consecutive cache lines, which is actually a strided access pattern. However, the address correlation over all the access buffers may not be meaningful at all, as evidenced by the memory addresses of the network packets in this sample sequence. Instead of predicting the memory references, we can rely on the information already available in the data item descriptors in the queues. The descriptors, as shown here, at least contain the pointer to the associated buffer and its length, which can be used to resolve the future references for the purpose of prefetching. Let's take a look at the design of HyperData and how it works. The blue boxes in this figure show the components of HyperData, which I'm going to describe in the next couple of slides. The monitoring set in HyperData watches the queues for data arrival. It actually monitors cache coherence, write transactions to the doorbells associated with the queues, and triggers the prefetcher of the target core corresponding to the updated queue. The monitoring set must actually perform key value lookup operations where the key is the tag of a queue doorbell address and the value is prefetch information. Prefetch information contains the queue address as well as prefetch type, which specifies what part of the buffer should be prefetched. The monitoring set must be able to monitor on the order of 1,000 queues as there are several I/O devices and a multitude of tenants in a system. Our design choice for the monitoring set is a cuckoo hash table, which has fast lookup time and a small conflict rate, even with a small number of ways. To discover the exact memory locations that should be prefetched, HyperData's prefetcher must be instructed on the layout of the queue and descriptor data structures. The descriptors are typically stored in a circular array or ring, as shown in this slide. The prefetcher has programmable registers to store the offsets of the head and tail pointers of the ring, as well as the offset of the ring itself in the queue data structure, so that it can read the in-queue descriptors. For extracting the target addresses of prefetch requests, the prefetcher has another set of programmable registers to store the offsets of the address and length of the corresponding data item buffer in the queue data structure. The prefetcher is implemented using a finite state machine as shown at the bottom of this slide in order to traverse the descriptors and issue the required prefetch requests. We modeled HyperData's hardware in the Gen 5 simulator. We evaluated HyperData on both data plane cores which dispatch the network packets with different traffic shapes and queue formats, and also tenant cores which run a key value store application. HyperData is compared against a baseline and a stride data prefetcher, and we can see that it significantly improves the performance. The stride prefetcher can capture the access pattern within packets, that is, accesses to consecutive cache lines, but it cannot learn the temporal or spatial access pattern of packets within or across the queues. However, since HyperData resolves the exact memory references through the descriptors, it is not affected by such complex access patterns. As for conclusion, we were motivated by the fact that cache misses of accessing I/O or tenant data is a major bottleneck in data plane systems. We proposed HyperData to accelerate data transfer in data planes through targeted prefetching, where instead of trying to predict the complex access patterns, exact cache lines of data buffers are brought to the appropriate core's L1 cache. HyperData watches for data arrival in the queues through a system-level monitoring set, and the programmable prefetcher of HyperData discovers what cache lines must be prefetched by reading the descriptors of data items. Our simulation results showed that HyperData improves processing latency by up to 2.4 times with a small area overhead. Thank you very much for your time, and I hope you enjoyed this video.